Hello and welcome back for chapter 5/6. Chapter 5 is actually just a little intro into chapter 6. If you go into chapter 5 and look, they cover several distributions that we are not going to work with this semester. We're going to move into this continuous probability functions. And we're going to use a particular one. So a continuous probability function in general is the area under the density curve between 2 points. And so we're going to be looking at that, but our special curve that we're going to look at, the area under, is the normal curve, the normal distribution, using the empirical rule that we used back in chapter 2 towards the end. So that is a particular continuous distribution that we're going to look at. So continuous probability functions have to do with quantitative continuous data, whereas in chapter 4 we were dealing with quantitative data, but it was discrete. And then in chapter 3 we were dealing with probability, which is qualitative data. So we are in chapter 5 and 6, we're going to deal with quantitative continuous data. So if you have your chapter 6 notes out and open, the first thing we're going to talk about actually extends from what we did in at the end of chapter 2 with the empirical rule. So it says the standard normal distribution is a normal distribution of standardized values called Z-scores. A Z-score is measured in units of the standard deviation. So the Z-score basically is a way for us to compare apples to apples. So if I wanted to compare my height compared to my husband's height, he is absolutely much taller than I am, but we would probably make the comment that, wait, on average, females tend to be not as tall as males. And so I should be really comparing my height to other females, and he should be comparing his height to other males. And so that's called relatively comparing two values. And so what the Z-score does is it puts us into a relative comparison. So my Z-score would be me compared to other females' average height, and then my husband's Z-score would be his relative comparison to other males and their average height. So this is how we calculate it. It says if X is a normally distributed random variable and X is defined as normal. So we did B for binomial in chapter 4, and now this is going to be our normal distribution. With the parameters are the mean and the standard deviation, then the Z-score is going to be defined as this. Now, the symbols we're using here, X with this little hat, is the observed X, and then the mu and a sigma are for if we have population data, and if we don't have population data, we would use for sample data, it's going to be calculated very much the same way, except for we're going to have our observed X subtracting the sample mean divided by the sample standard deviation. And that's how we're going to calculate it. So the Z-score tells you how many standard deviations the value X is above or below the mean. So above the mean would be to the right of the mean, and below the mean would be to the left of the mean. So it says, what is the Z-score of X when X equals 1, and X is defined as a normal distribution with mean 12 and standard deviation of 3. So we would say that the Z-score is 1 minus the mean of 12 divided by 3, which is a negative 11/3, which is approximately 3.67. So 3.67. And then if we remember, when we go back to the empirical rule, that is very unusual. It's very far from the mean, and it's negative. So underneath the mean, so it's to the left. Okay. So it says fill in the blank. Jerome averages 16 points a game with a standard deviation of 4 points. This X is distributed normally with a mean of 16 and 4. Suppose Jerome scores 10 points in a game. His Z-score is a negative 1.5. So how would we describe this? It says that this score tells you that X equal to 10, he made 10 shots, is 1.5 or negative 1.5 standard deviations to the left of the mean, which is 16. So we would visualize it like this on the curve that we learned about. If the mean is here, then his 10, X equal to 10, is over here to the left. So let's just spend a minute and kind of go back through our empirical rule that we learned about at the end of chapter 2. And the empirical rule says that about 68% of the X values lie between 1 standard deviation below and 1 standard deviation above the mean. About 95% of the X values lie between 2 standard deviations below and above the mean, and about 99.7% of the values lie below and above by 3 standard deviations. Okay, so we would call the standard deviations the Z-scores. That's essentially what we're calling them. And those are shown in the graph here below, where we have 34 and 34%. And then we've got 13.5, 13.5, 2.35, 0.15%. Okay, so this is where our 68% falls. And this is where our 95% falls. And then we also made the comment back in chapter 2 that anything that falls outside of 2 this way is considered unusual. And anything that falls this way, so 2.5% this way, 2.5% that way, or 2 standard deviations that way and 2 standard deviations this way, are both considered unusual outcomes. So let's look at some examples. So it says the mean height of 15 to 18-year-old males from Chile from 2009 to 2010 was 170 centimeters with a standard deviation of 6.28 centimeters. It says male heights are known to follow a normal distribution. So let X be the height of a 15 to 18-year-old male from Chile. Then X can be distributed as normal with a mean of 170 and the standard deviation of 6.28. Suppose we have a male from Chile that is 176 centimeters tall. The Z-score when X is equal to 176 is. So we are going to calculate that, and that's 176 subtracting the mean, which is 170, divided by the standard deviation, which is 6.28. And then I'm going to take parentheses 176 minus 170 to make sure that's calculated first, because it's in the numerator, divided by 6.28. And it looks like that Z-score is 0.9554. And it's positive, so 0.9554. So this Z-score tells you that X equal to 176 centimeters is 0.9554 standard deviations to the right, because it's positive. Because it's positive, of the mean. And that is, the mean, it was 170. So it says, suppose that the height of a 15 to 18-year-old man from Chile from 2009 to 2010 has a Z-score of Z equals a -2. What is the male's height? The Z-score of Z equals a -2 tells you that the male's height is, and we're going to fill this in. So there's a couple ways you can look at this. We can say that we know that if we take 170 and it says it's a negative, we know it's underneath it's less than the average, and I can just subtract 2 of the standard deviations. That's one way to do that. And we get 157.44 centimeters. Now, if that male did not fall at an integer number for standard deviations, it would entail something a little bit more technical. So we should probably use the equation that we have for Z-score. So we know the Z-score equals a -2. We don't know the actual observation. We know the mean is 170 and the standard deviation is 6.28. So to solve for this X, we can multiply both sides by 6.28. So a -2 times 6.28 gives us a -12.56. And if we add 170 to both sides, it would tell you that that observed height of that male is indeed 157.44 centimeters. So a formula that you could use anytime you're asked to solve for the X observation, you could say it is the Z-score multiplied by the standard deviation, adding the mean. So that might be a good piece to write down for your exam. Let's look at another example here. So it says in 2012, 1,664,479 students took the SAT exam. The distribution of scores in the verbal section of the SAT had a mean of 496 and standard deviation of 114. Let X equal an SAT exam verbal section score in 2012. Then we know that X is distributed normally with mean of 496 and standard deviation of 114. Find the Z-scores for these two people, these two scores, students, and interpret each Z-score. So I'm going to say Z1 is equal to 325 minus 496 over 114. And we know that that student scored underneath the mean by -1.5 standard deviations. So let's say student 1 scored 1.5 standard deviations below the mean of 496. Let's look at student 2. Student 2, they scored 366.21 minus 496 over 114. And make sure that you're practicing doing these as I'm doing them so that you can make sure that you understand. And if you don't, you can send me a message asking questions. This is he too scored, or she scored underneath the mean, but it was only 1.14 standard deviations. So student 2 scored 1.14 standard deviations below the mean. Okay. The next one says, suppose X has a normal distribution with mean 25 and standard deviation of 5. Between what X values do 68% of the values lie? Okay, 68%. The cool thing is we know that from our curve that we learned here, that 68% falls between a -1 and 1 standard deviation. So if we know our mean is at 25, we know that those values are 68% fall in between those. And so that would be subtracting 1 standard deviation, so 20, and adding 1 standard deviation, so 30. So between 20 and 30. Let's do another comparison. It says the scores on the college entrance exam have an approximate normal distribution with mean 52 and standard deviation 11. It's asking us about 68% of the values lie between what two values, 95% and 99.7. And these are all of those special markings on the curve that we learned about. The 68, the 95, and then the 99.7. So it's just the -1, -2, -3, and then +1, +2, +3 standard deviation. So let's go ahead and draw those. For me, filling out the curve first makes it easier to answer the questions above. So I'm going to put my center always at the mean, so 52. And then we have 34% to the left and 34% to the right. And so that's 52 minus 11 is 41. And then 52 plus 11 is 63. And so that's our 68% up here. So these values are 41 to 63. And that's plus and minus 1 standard deviation. And then we go another standard deviation, and that's the extra 13.5%. And so we again subtract 11, which is our standard deviation. So that's 30. And we add 11, which is 74. And that makes up our 95%. If we add 13.5, 34, 34, and 13.5. And that is plus or minus 2 standard deviations. And then the last marking that is important is the third standard deviation, and that's where we get the extra 2.35% on both sides. It still leaves 0.5% here and 0.15% here. But again, we subtract 11 and we get 19, and we add 11 and we get 85. So between 19 and 85 is plus or minus 3 standard deviations. And that is the end of lesson 6.1. So catch me back for lesson 6.2 here in just a bit.